Well, today I'm in the house. I'm not driving. I still did all my driving that I normally do, but today I decided to switch it up. And instead of just sitting in my car and chatting with you guys, I thought, why don't we work on this? Go ahead and do the question that I did yesterday. Now, to some of you, this question might not have been yesterday, but so that's why I put it on here. All right, so what we had here was we have this double bond, we have this chloride, and then we have water and we have sodium carbonate. And yes, if you're wondering, that's supposed to be Na2CO3, not just NaCO3. So we could also look at this as an allylic system. So now this is what I would do if I have a question like this, and this is based off of my Organic Chemistry Simplified series. I put it together, it's a 6-post series, and this would be number 5, where I talk about the reaction scheme. And what I tell students is, if let's say, for example, you're just not sure exactly where to start, if you have one thing above the arrow and one thing below the arrow, you want to focus on what's above the arrow and you can just disregard what's below the arrow. Okay, that's the quick way of going at it. Now let me go into a little bit more detail. So if we look at this, we can clearly see this is a base, and then we've got water, which can also act as an acid. So we would think that maybe these two things would come together and we would wind up getting OH minus. Now the problem is you're probably going to get a small percentage of that, but the thing is this is a weak base, so there's not going to be a lot of that. So what you want to do in this question is consider as though that base is not even there, and I'll show you where I think that this is coming into play, okay? So just imagine that this is water. Now since we focus on just what's above, if it's water, then we know that if we have a neutral molecule with an alkyl halide, that we're going to do one of the 1 mechanisms. And typically if it's like an alcohol type base, that's what I tell students, and you can go on my Instagram and get that SN1, SN2, E1, E2 cheat sheet. So this is kind of like an alcohol. It's going to go SN1. So what's happening here? So in this case, if we look at this, we can see that what we'll wind up doing is generating a carbocation. Because we know if we have a negative charge, we're not going to generate a carbocation. So in this case, we're going to wind up getting this structure right here. Okay, that would be pretty simple to think about. If we know, imagine if we didn't have this, we'd know that we would wind up losing the chloride, getting the carbocation. Now at this stage, we can see what's happening here is that we've got this carbocation, but it's also in conjugation. So we're going to have to consider 2 different resonance structures where we can flip that double bond down here, and now our positive charge, whoops, will be right there. These are the 2. Now I'm pretty sure all of you know this, but I just want to point this out, is that you actually don't have this resonance structure and that resonance structure. It's actually a mix in between, but we draw this way to kind of get conceptually or an idea of what's going on. So we can see here that what's going on in this case is that we've got a secondary carbocation here, and we have a tertiary carbocation here. Now out of the carbocation behavior, we know the tertiary is going to be more stable. So then to finish this off, it's pretty easy at this point once we understand that. So then we're going to wind up getting the chloride here and our double bond. Oops, sorry. Jeez, the chloride, what am I doing? Water attacks. So we'll wind up getting our OH after the mechanism's all done. So we wind up getting an attack here, okay? Now, one other thing that I want to address here is that, so let me do this. We don't need all this now, so let me just get rid of this. And actually, let's do it this way. So let's just go ahead and draw the product up here. So there, and let's actually use all blue, and we'll get an OH there. Okay, so let me just make sure I got reoriented here and make sure that I actually draw the right product. Sometimes I do this too quick. All right, and we said that this is going to go via an SN1. So, and I just want to kind of bring this up again, so I kind of just talked about it, but the key here is that between these 2 things, there's going to be a very small percentage of OH minus, okay? Now, when you first initially looked at this, and if some of you were pulling this off of my cheat sheet, I would initially agree with you in the fact if you just looked at my cheat sheet, you saw that there's a negative charge. I say if there's a metal or a negative charge, you're going to have the 2 mechanisms. And then if you've got an O minus, in this case, you're going to get an E2 mechanism. So in that respect, yes, this is a little tricky in the fact that then what you have to do is you have to look at the actual base that you're generating. So in this case, or sorry, the base you're using. So this base is very weak. So in this case, we're going to get an SN1. So that's why, for example, we are not going to have an SN2 because this is not a really good nucleophile, or it's not going to generate one. And the other thing is people brought up, which is a really good point, is why not an SN2 prime? Which means, for those of you that aren't familiar with that, is that you essentially tack this position the double bond flips down and then kicks it out. So instead of attacking directly, you kind of indirectly attack it through the pi system or through the electronic system. It's for the same reason that we're not generating a really strong negative charge. Another thing somebody said is, why couldn't we get, for example, like an E1 elimination or maybe even some sort of E2, so elimination? Same factor. So we can see that all of these right here, these all depend on really a strong negative charge, or not. We need a really, I guess, a decent negative charge. And what's happening is under these circumstances, we don't get that. So what we want to think about here is that since this is weak, that we're going to generate a carbocation, and then we have to look at the system overall. But those are really good points. This actually sparked a discussion much more than I thought it was going to, so this actually worked out to be a great question. But overall, what it's going to be is it's an allylic chloride, and you get an SN1 mechanism, and you wind up getting it here. I guess one other point, I just thought about it and just left my mind. Give me a sec here. Oh, okay. This is, oh yeah, somebody brought this up, and this is great. So I want to draw this because this also gives a really good understanding here. All right, so let's do bromide. And this person showed me this example, which I thought was really cool. And I can see why. I should talk about this as well. So they had a phenol, and they treated that with, if I'm not mistaken, I got to go back and remember, but I'm pretty sure I think it might have been the same base or a similar base. And they got an O minus. And in this product, we'll just put phenyl. They wound up getting just a simply, in this case we can see, would be an SN2 product. Now this is when we start getting into examples like this. Well, first let me say it this way. So that cheat sheet that I have on my Instagram, that from my experience over the past 19 years holds pretty good. I mean, you can essentially take that and that will answer a lot of the questions. But you know, with any cheat sheet or any kind of guide, there's always going to be exceptions. And this is one of those things that falls in where the whole point of this comes into all of those details that you learn in SN1, SN2, E1, E2 in terms of the leaving group, the substitution. So what's happening here is, in the top case, is that this base is not strong enough to generate something to do in SN2, so we wind up doing an SN1. In this case, what we've got here is we don't really have a strong negative charge because we've got all this resonance. But the thing is the bromine is a good leaving group and this is a primary. So this was a really good point to bring up, and I'm glad that this person did. That in this case, you can see that what's different. This is a primary with a bromide. We've got a secondary with a chloride. And those subtle differences there, right, there sometimes can make a difference, okay? So this, I just wanted to point that out at the end. This was a really good example because when I first did this, they said, well, it must do an SN2 based off of this. But it doesn't look like much, but a primary bromide versus a secondary chloride can make a difference, and obviously it does here. So what about the base? If the base is in there and it's not really doing anything, that's sodium carbonate, and it's not strong enough to really generate anything, what's really the point? So I'm not going to draw this out, but I want you guys to kind of look at your example that you wrote out and think about it and see. But the sense that I get in this is the fact that when you generate this molecule, when you add water and you lose the alkyl chloride, you know you generate HCl, right? What's going to happen if you have HCl in the presence of a double bond? You're going to get an addition reaction. So I'm pretty sure that that base is in there to soak up the acid so you don't get two reactions. You only want one.